continuing with our review sheet, we're going to look at 29. As the car moves from its present position to position X, its kinetic energy. Now, because the car is moving in a circle, the speed is constant. And because kinetic energy is 1/2 mv squared, if we look back at the picture from the last one, we'll see because the speed remains the same, the kinetic energy is going to remain the same, so the choice is C. All right, number 30. A mother pushes her 120 Newton child who is sitting on a swing. If the mother exerts a 10 Newton force on the child for 0.5 seconds, what is the magnitude of the impulse imparted to the student? So they're asking me for the impulse. So right away I'm going to say, what is impulse? Well, impulse is equal to the change in momentum. And I know impulse is equal to Ft, which is m delta v. But now I'm going to say, well, what am I given in this problem? Well, I'm given the weight of the child, F of g. I'm given the force the mother exerts, so F is equal to 10 newtons. And I'm given the time, which is equal to 0.05 seconds. So if I want to find the impulse, I can just say that delta P is equal to Ft, and I don't need to know how much the child weighs. I don't need to know that. So I can say that delta P is equal to Ft, which is 10 newtons times 0.5 seconds, which comes out to be 5 newtons times a second. Now remember that a lot of these problems, you can do the math in your head. So even though you're going to have your calculator, I would still kind of estimate the answer in your head, and you can multiply 10 divided by 0.5. Everyone should do that. So remember, we can make mistakes pressing the wrong button, so just kind of ballpark it in your head. All right, so the answer to number 30 was A. Number 31, a 2 Newton force acts on a mass if the momentum of the mass changes by 120 kilogram meters per second. That's the change. So the change is going to be delta P, which is going to be 120 kilogram meters per second. So that's delta P. The force acts on it for a time of, so I want to find the time. So again, I'm going to use my impulse momentum. So delta P is equal to Ft, and I want to solve for T. So I'll rearrange the equation to solve for the unknown in terms of the known so I don't make an algebra mistake. Because if I did the wrong algebra, that's going to be one of the wrong answers. And I'll show you what I mean. So when I rearrange this equation, I get that T is equal to delta P over F. So delta P is 120 divided by F, which is 2 newtons. Now again, do you see how you could do this in your head? 120 divided by 2 is 60. And remember, a newton is a kilogram meter per second squared, so my kilograms cancel, my meters cancel, 1 of the seconds, and 1 over a second is a second, which is the correct unit for time. If you carry your units through, you have a foolproof way in physics to always check your work, and then you would catch those algebra mistakes. Now, so the correct answer is 60. So what if you, if you multiply, then I'll have that answer. But they have other choices. So anyway, number 31, the answer is 60, which is choice C. Number 32, a 2 kilogram ball is traveling north at 4 meters per second and collides head-on, so it's going north at 4 meters per second, and it collides head-on with a 1 kilogram ball traveling south at 8 meters per second. What is the magnitude of the total momentum of the two balls after collision? Now remember that momentum is a vector quantity. It has both magnitude and direction. I have to take the direction into consideration. So I'm going to use my standard Cartesian sign convention that says up and to the right is positive. So what is my momentum? Well, the first one is 4 meters per second times 2 kilograms. That's my momentum because P is equal to mass times velocity. Then the other one is 8 meters per second times, and this is negative because it's going south, times 1 kilogram. So I get positive 8 plus negative 8. So because they're going head on, the total momentum is going to be 0. They're going to cancel each other out. Now, if I wanted to write it all out, I could say like momentum of A plus momentum of B is equal to the momentum total, or 1 plus 2. But again, you can say you have to be aware of the sign. So this is going north is up, which is positive. This one's going south, which is down, which is negative. All right, number 33. It says the total momentum of a system that consists of a moving rock and an exhaust will remain the same. And this one is just an example of conservation of momentum. Number 34, the diagram below shows 2 carts initially at rest on a horizontal frictionless surface being pushed apart when a compressed spring attached to one of the cart is released. Now, initially, it says both of these are at rest. So the momentum of the one cart is going to be equal and opposite the momentum of the other cart. Now, we could write out our whole equation, for momentum, like MAVA plus MBVB is equal to MAVA prime plus MBVB prime. But both initial velocities are 0. So when I move this to the other side of the equal sign, minus MBVB prime is equal to MAVA prime. We see that the momentum of ball B, or whatever the cart is going to be equal and opposite the momentum of the other one. So whenever we see a problem like this, we don't have to write it all out. We can just look at this and we can say to ourselves, you know what? I know that this momentum is going to be equal and opposite of this momentum. So I can just look right on here and say 6 times 1 is equal to 2 times x. Well, 6 times 1 is 6, and 6 divided by 2 is going to be 3. So this is actually a really simple problem. Number 35. A 3-kilogram man is traveling in a circle with a 2.2 meter radius. So the mass is equal to 3 kilograms. He's traveling in a circle. The radius is equal to 0.2 meters. And the speed is equal to 2 meters per second. What is the centripetal acceleration? So centripetal acceleration is v squared over r. So it's 2.0 meters per second squared over the 0.2 meter radius. So 2 squared is 4, so 4 divided by 0.2. Now remember, you could do this in your head. So even though you're going to do your calculator, you're going to be using it, you want to ballpark the math in your head in case you press the wrong button. Now, whenever you have a decimal in the denominator, if you just move everything over, and if I said 40 divided by 2, can I easily do 40 divided by 2 in my head? So that's the trick to doing math in your head if you have a decimal in the denominator. So I know 40 divided by 2 is 20. And then I have a meter squared over a second squared divided by a meter, which is a meter per second squared, which is the correct unit for acceleration. So the answer to number 35 is B. Number 36, what is the centripetal acceleration of a ball traveling? So I want to find centripetal acceleration is traveling at 6 meters per second in a circle with a radius of 9 meters. So centripetal acceleration is v squared over r. It's the same thing. So it's 6 squared over 9. So 36 over 9. Can I do that one in my head too? Sure, that's 4. So again, you have your calculator, but you're going to check your work. Number 37, an object travels in a circular orbit. If the speed of the object is doubled, its centripetal acceleration. So the way to always do these is first you write down your basic equations. Centripetal acceleration is v squared over r. It says if the speed is doubled. So now, instead of v, I have 2v squared over r. Well, when I multiply all this out, when I square this, I get 4v squared over r. So the difference between the original equation and this one is 4. So the answer is quadrupled because it's 4 times as much. And that's the way you do those. You don't do it in your head. You write down the equation, and then you substitute in how the equation changes. All right, let's go to the next page. So now we see that we have a diagram, and it says base your answers to questions 38 through 42 on the diagram below, which represents a 2 kilogram mass. It's placed on a frictionless track at point A and released from rest. Assume the gravitational potential energy of the system to be 0, point E. So point E here is my base level, because they're telling me that the potential energy is 0. So right away when I look at this, the first thing that's I'm going to say in my mind is, I bet you I'm going to be doing conservation of energy. So question 38 says the gravitational potential energy of the system at A is, well, I know potential energy is equal to mgh. So it's equal to the mass times the acceleration due to gravity, 9.8 meters per second squared, times the height, which I'm going to see is 40 meters. Now, I would ballpark this in my head. I would say 2 times 10 times 40. So 10 times 40 is 400, times 2 is 800. Do I see that as a choice? Right here, choice C. Number 39, compared to the kinetic energy of the mass at point B, the kinetic energy of the mass at point E is, so here's point B, and here's point E. So kinetic energy is going to be, now you have to read this carefully. They say compared the kinetic energy of the mass at E is, so remember, here I have, it's all potential. Whatever I lose in potential, I gain in kinetic. So here, it's halfway, right? So I'm going to lose half my potential energy, and this is going to then, whatever I lose in potential, I gain in kinetic. So from here to here, it's also half. So this is going to be twice as great, because whatever the kinetic energy here is, it's actually going to be all kinetic here. So this is the total, which is 40. So this is halfway, and then this is another half. Number 40. As the mass travels along the track, the maximum height it will reach at point E will be closest to. Now, first of all, you have to realize there's no friction. But even though there's no friction, can this mass go higher than it started? No. So no matter what, it can't go above this point. It can't go higher than when it started. Conservation of energy. So the highest it'll be able to reach is going to be D, 40 meters. (41) If the mass were released from rest at point B, so if it was released from here, its speed at point C would be, so point C and point B are at the same height. So if this is where it starts off at rest, this is the highest it's going to come to, so when it gets to this point, the velocity is going to go back to 0. So that's why the answer is A, 0. I mean, you don't even have to do calculations for these. The whole thing with these questions are, do you have a conceptual idea? Do you understand conservation of energy? All right, number 42. Compared to the total mechanical energy of the system at point A, the total mechanical, remember mechanical energy is the sum of the potential and kinetic. The total mechanical energy at F is, the answer is, it's going to be the same. Because it doesn't matter if it's A, B, C, I guess there's no D, E, F, whatever. Any point, the total energy is going to be the same. Now, the amount of potential and kinetic aren't going to be the same, but the total is always going to be the same everywhere. All right, let's switch to this side now. Oh, so the answer here was C. All right, number 43. If the kinetic energy of a 10 kilogram object, so the mass is equal to 10 kilograms, is 2,000 joules, its velocity is, so we have to know that the equation for kinetic energy is 1/2 mv squared. And instead of just plugging the numbers in the formula, I'm going to rearrange the equation to solve for the unknown in terms of the known. So I'm going to multiply both sides by 2. I'm going to divide both sides by m. And then I'm going to take the square root of both sides. Now, the most common mistake people would make is they're going to forget to take the square root. So it's 2 times 200. Oh, it's 2,000. 2 times 2,000 over the mass, which is 10. So it's going to be the square root of 4,000 over 10, which is the square root of 400, but the square root of 400 is 20. If I forgot to take the square root, is that one of the choices? If I forgot to multiply by 2, is that one of the choices? So the most common mistakes you're going to make, that's going to be the some of the choices. So you want to make sure you don't do those. And that's why you do the review sheet yourself and you don't just look at the solutions. Number 44. When the speed of an object is halved, what happens to its kinetic energy? So I know kinetic energy is 1/2 mv squared. So if I now half the speed, so now I'm going to say kinetic energy is 1/2 of m v over 2 squared. Now I multiply that out, so it's 1/2 of m, and then it becomes v squared over 4. So it says what's going to happen. So now I compare this to this. So I'll just leave the 1/2 and everything the same. The difference is I have a 4 in the denominator. So if I have a 4 in the denominator, that means it's going to be quartered. And the answer is A. Number 45. As a ball falls freely toward the earth, its kinetic energy. So I know kinetic energy is equal to 1/2 mv squared. So a ball starts to fall. Well, initially the velocity is 0. Gravity is pulling it down. So because gravity is pulling it down, the velocity is going to increase, increase, and increase. So here the velocity is going to increase. I see velocity and kinetic energy is directly proportional. So as velocity increases, the kinetic energy is also going to increase. If you write down the equation, it helps you to visualize it because most people are visual learners. Number 46. A 20 Newton block falls freely from rest from a point 3 meters above the surface of the earth. What is the gravitational potential energy? So after it's fallen 1.5 meters. So potential energy is mgh. Well, if it starts off at 3 and it falls 1.5, the distance above the earth it went is going to be 1.5 meters because 1.5 plus 1.5 is 3. So potential energy is mgh. So mg is the weight times the height it is above the ground. So potential energy is the weight, 20 newtons, times the height above the ground, which is 1.5 meters. So that comes out to be 30 joules. Number 47. Which graph represents the relationship between the potential energy and the height above the ground? So let's look at my equation. Potential energy is mgh. So my graphs all have the height. So as my height is going to increase, what happens to my potential energy? It's also going to increase because I see these are directly proportional. Now, is this height squared? No. So this correlation is a direct linear graph, because as this increases directly. So I can just easily eliminate all the wrong choices, and there's my graph. So again, if you write the equation down, the equation helps you to visualize and see what the answer is. All right, next page. Number 48. So we see we have a graph. Below is a graph representing the elongation. That's how much a string stretches of a spring at different forces added to it. What is the value of the spring constant? So now I'm going to apply Hooke's law. F is equal to kx. So k is equal to f over x. So f is going to be, now I'm going to have to look at the graph. Okay? So what I do is I always, in this case, because it goes through 0, I always look at endpoint. This is a straight line. So I'm going to do the force, which is going to be 5 minus 0, over the elongation, which is going to be 0.5 minus 0. So 5 divided by 0.5, so k is equal to 10. Now force is measured in what? Newtons. X is equal to this, so it's Newton times a meter. What if you didn't look at the units? Would you put choice C? You see how C and D look exactly the same except the units? You have to be careful. Number 49. A student performed a laboratory investigation to determine the spring constant of a spring. The force applied to the spring was varied, and the resulting elongation of the spring was measured. The student graphed the data. So we're going to do the same thing to find x. So F is equal to kx. K is equal to F divided by x. So I'll probably just choose my endpoints because it's easier. So I'm going to say 16 minus 0 over 0.8 minus 0. This is a Newton. This is the meter. So K comes out to be 20 newtons times a meter, which is choice D. Number 50, a person, oh no, 50, yeah. A 2.2 kilogram mass is pulled by a 30 Newton force through a distance of 5 meters, as shown in the diagram. What's work? Well, work is equal to the force times the displacement, but it's only the force acting in the direction in which the object moves. So I don't need to know the mass. So work is equal to the force, 30 newtons, times that displacement, which is 5, and I can do that in my head. 30 times 5 is 150, and it's a newton times a meter, and a newton times a meter is also called a joule. Number 51. The diagram below shows a 5 kilogram mass sliding 9 meters down an incline from a height. The object gains 30 joules of kinetic energy. So we're going to do conservation of energy. How much work is done against friction? Well, at the top, my total energy here is going to be mgh. So it's going to be 5 times the height, 2, times 9.8. So my total energy up here is 98 joules. At the bottom, they told me that it gains 90 joules of kinetic energy. Well, at the bottom, we know that the potential energy is 0. But there's only 90 joules of kinetic energy. So what happened to the other energy? Okay, the other energy was the work done by friction. So when it says how much work is done against friction as the mass slides, well, if I have 98 here and 90 here, the difference is 98 minus 90, 8 joules is done by friction. Number 52, if 700 watts of power, so power is equal to 700 watts, is needed to keep a boat moving through the water at a constant speed of 10 meters per second, what is the magnitude of the force? So I know power is equal to work divided by time, but power is also equal to F times V. So F is going to be P over V, so 700 divided by 10 is going to be 70 newtons. Number 53, a motor having a power rating of 500 watts, so the power is 500 watts, is used to lift an object weighing 100 newtons, so that's my weight. How much time does it take the motor to lift? So I want to find time. So again, power is equal to work divided by time, which is FD over T. Now this is a vertical displacement. So I'm going to rearrange the equation to solve for the unknown in terms of the known. So T is going to be equal to FD over P. So it's going to be 100 newtons times 10 meters divided by 500 watts. So this comes out to be 2 seconds. Remember, rearrange the equation to solve for the unknown in terms of the known. Number 54. A person does 100 joules of work, so this is the work, while pulling the string of a bow. What will the initial speed be? Well, I know that work is equal to the change in kinetic energy. So work is equal to 1/2 mvf squared minus 1/2 mvi squared. So initially it's going to be 0, so I just have to find that work is equal to the change in kinetic energy, which is 1/2 mv squared. So now I want to solve for V. So I'm going to rearrange the equation, and instead of calling this W, because work is equal to the change in kinetic energy, I can call this K if I want. So I'm going to multiply both sides by 2. I'm going to divide by M, and then I'm going to take the square root of both sides. So it's 2 times 1,000 joules divided by 0.5 kilograms. So the velocity, the speed comes out to be 20 meters per second. Now, if you forgot to take the square root at the end, that's going to be one of the choices. If you forgot to multiply by 2, that's going to be one of the choices. So again, when you rearrange the equation to solve for the unknown in terms of the known, you're less likely to make a mistake. Number 55. As the pendulum swings from position A to position B as shown, so here's A. Now, you already know you're going to do conservation of energy. What is the relationship of the kinetic and potential energy? So I would call this my base level. Here's at the top where it's starting. Over here, I can see that it's going to be all potential, because if it's not moving, the kinetic is going to be 0. As it starts to swing, whatever I lose in potential, I'm going to gain in kinetic. All right, so now I'm going to look at the questions. So as the pendulum swings from A to B, what is the relationship of the kinetic to the potential? So I would read all the choices, and the correct choice is choice D. The kinetic energy increase is equal to the potential decrease. Whatever I lose in potential, I gain in kinetic. Number 56. Which pair of concurrent forces could produce a resultant having a magnitude of 10 newtons? So whenever I have two forces, the one rule for forces is we know that vectors are added head to tail. But what I'm looking at now is I want to know which one could possibly be 10, so I have to look at the minimum and I have to look at the maximum. And I could have an infinite number in between. So how do I find the minimum and the maximum? What I do is the minimum is going to be when I subtract them, and the maximum is when I'm going to add them, and then I can have an infinite combination between. So 10 plus 10 is going to be 20, and 10 minus 10 is going to be 0. So for choice A, it's going to be range from 0 to 20. Choice B, 30 minus 10 is going to be 20. 30 plus 10 is 40. I add these up, 0 to 9.4, because when I subtract them, it's 0. When I add them, it's 9.4. When I subtract these, I get 0.3, and when I add them, I get 9.7. So which one of these has an answer of 10? The only one that could possibly have an answer of 10 is going to be the first one. So that's how I answer these. I find the minimum and the maximum value. So I add and subtract. All right, number 57. The diagram below represents two forces acting concurrently on object P. Which diagram represents the resultant? So the resultant is what happens when I add vectors. Vectors cannot be added algebraically. Vectors have to be added vectorially, which means I have to add them head to tail. Does it matter the order? No. So let's say I take the first one, which is 10 newtons. From the head of this one, I put the tail of the other 6 newtons. From where I start to where I end up is my resultant. And I would use the Pythagorean theorem. But I don't have to calculate. They just want a picture. So when I look at the picture, the choice on the picture is choice D. What if I did it the other way? What if I first drew the 6 Newton vector, and then from the head of that vector, I did the tail of the 10 Newton vector, and then from where I start to where I ended up, I drew my resultant. Does it look exactly the same? Does it point in the same direction? It does. So it doesn't matter with vectors. I could do A plus B or B plus A. I'm still going to get the correct answer. Okay, number 58. Number 58 says the diagram below represents a constant force F acting on a block located on a frictionless horizontal surface. As the angle between the force and the horizontal increases, what happens to the acceleration? Well, I know that F is equal to ma. So now, what force is going in this direction? So it's the horizontal force. So again, here's my force. When I have the components are added together head to tail. They're perpendicular to one another. That's just plain F. So this is my horizontal and this is my vertical. So my horizontal component, FH, it's adjacent to my angle. So it's going to be F cosine theta. So it says as the angle increases. So as this angle increases, what happens? It's going to decrease. So if you wanted to, on your calculator, you could just make up angles, like put in 30, put in 60, and see how that changes. Okay? Some of you in your math class, you have to memorize, like, you know, the cosine of some various angles. When you had to do the unit circle, didn't you have to memorize that for a class? Yeah. Do you still remember it? I don't know. Okay, number 59. A force of 100 newtons is applied to an object at an angle of 30 degrees. What is the magnitude of the vertical component? So again, this is my horizontal component. My vertical component looks like this. If I look at my picture, my vertical component is opposite the 30-degree angle. So F vertical is equal to 100 newtons times the sine of 30 degrees. If you're not sure how to do this, just write out the definition. Sine of theta is opposite over hypotenuse. Sine of theta is opposite FV over the hypotenuse F, which is 100. So 100 times the sine of 30 is equal to FV. So when I do that on my calculator, it comes out to be 50. Number 60, which quantity is vector? A vector quantity has both magnitude and direction. Distance is scalar, speed is scalar, time is scalar, so my answer is C. Which two terms represent a vector quantity and the scalar quantity of the vector's magnitude? So we want ones that are related. So acceleration and velocity don't measure the same thing. Weight and force are both vectors. Speed and time are totally different. So distance and displacement, D. All right, let's flip over to the next page. Base your answers to questions 62 and 63 on the diagram below, which shows a 1 kilogram stone being dropped from a bridge 100 meters above the gorge. What is the weight? So I don't even have to know the picture. I know that weight, F of G, is equal to mg, so it's equal to 1 kilogram times 9.8 meters per second squared, so 9.8 times 1 is just 9.8. I could do that in my head. Number 63, which graph of a distance traveled versus time graph represents the motion of a freely falling body? If something's in free fall, that means it's accelerating. Well, on a position versus time graph, acceleration is a curve. So I don't even have to look at these. Boom, I can do that answer in a few seconds. Number 64. If the mass of an object could be doubled, the inertia of the object would also be doubled, because we know mass and inertia are directly related. Number 65. Two forces are applied to a 2 kilogram block on a frictionless horizontal surface as shown in the diagram. The acceleration of the block is, so Newton's second law says F net is equal to ma. So A is going to be F net over m. But I have to look at this and get the net force. So I have to say, what is my sign convention, which I'm going to use the standard Cartesian sign convention, that up and to the right is positive. So if I'm calling to the right positive, so I have 3 newtons minus 8 newtons over my mass, which is 2 kilograms. So 3 divided by 8 is not negative 5 over 2, so I get negative 2.5. Now remember, minus is just, your negative sign just helps you to understand the sign. That's not an answer. So according to my sign convention, negative means to the left. So my answer would be 2.5 meters per second squared to the left. So the answer there is choice B. Number 66, which two graphs represent the motion of an object on which the net force is 0? So first of all, I'm going to say to myself, the net force is 0. What does that mean? Well, if the net force is 0, that means the acceleration is 0. Okay? So the next thing I'm going to do is I'm going to look at my graphs, and I want one where the acceleration is 0. So first I could look at this and say, well, curve represents an acceleration on a position versus time graph. So I can eliminate those choices. Now, both of these show something that have a 0 acceleration, but now I have to look at the next graph, and if the acceleration is 0, that means on a speed versus time graph, it stays at a constant speed. So then I can eliminate that, and then my choice is going to be choice B. And then the last one, number 67, it says the force required to accelerate to a 2 kilogram mass 4 meters per second squared is, so this is just Newton's second law, F is equal to ma. So it's 2 kilograms times 4 meters per second squared. I can do that in my head. 2 times 4 is 8 newtons. And that's it. And that's it. So now we did up to 67 in this segment.